again, students all over Bhutan. I hope you enjoy watching your e-education television programs. And here's another one from me, all about physics. And this lovely painting of Paro Dzong. That's not what I'm going to talk about, but I couldn't resist showing you because Paro Dzong is so beautiful. And remember what I said in a previous program, when this was being built, Galileo was wandering around Italy, finding out all sorts of new things. So I'm not going to talk about Paro Dzong, beautiful though it is. What I'm going to talk about today is capacitors. And let me show you some pictures of capacitors, which should, with luck, here we are on my computer. I hope you can see them. This is what capacitors look like. They come in all shapes and sizes, just like school students. There are some great big ones. There are some very tiny little ones. These are all capacitors. And on the side of the capacitor just there, you can see written 4700 and then a Greek letter mu, F. That means 4,700 microfarads. And it's meant to operate at 35 volts. Here's another capacitor. This one is meant to operate at 400 volts. So capacitors come in different sizes. They also come in different capacitances because the quality a capacitor has is called capacitance. Well, now, these are all different sorts of capacitor, but some capacitors, for example, the capacitors, hundreds of which are in your mobile phone, are tiny, almost invisible. Some can only be seen with a microscope, and they are imprinted onto the little electronic circuit board that makes your mobile phone or your computer work. Some capacitors can be almost as big as this room. So capacitors can be very big and they can be very, very, very tiny. And so what does a capacitor do? Where do we find capacitors? We find capacitors in almost every electronic device, whether it's your mobile phone, whether it's your computer, whether it's, for example, a touch switch, which works just by you not pressing it, but being near it. It works, for example, in timing circuits, where something just goes on for so many seconds or so many minutes and then stops. It works, for example, in defibrillators, which are things which you find, especially in a hospital. If somebody has a heart attack, you put two pads on their chest and then, boomf, a dirty jolt of electricity goes through them and starts the heart again. You find capacitors absolutely everywhere. So, here are capacitors, all shapes and sizes, but what do they do? Well, there's a bit of a problem here, and you need to be a bit careful. Some books or people will say capacitors store charge. They don't really store charge. What a capacitor stores is energy. How does a capacitor store energy? Well, it stores energy by separating the positive charges from negative charges, protons from electrons. They're all muddled up together, but we can separate them out. Just like my granddaughter here, I gave her a bag of multicolored sweets, and she is now busy separating out the red sweets from the green sweets. So this is exactly what happens in a capacitor. You're separating out the positive charges, the red sweets, from the negative charges, which are the green sweets. So if you think red sweets positive charge, green sweets negative charge, she's separated them out. They were all mixed up, and in order to separate them out, she's had to use energy. So to make energy stored in a capacitor, you have to provide the energy. And quite typically, you will supply the energy from a battery or some other device. It could be the mains. And a capacitor, therefore, stores energy. How does it store energy? It stores energy by the separation of positive and negative charges. A battery stores energy. It stores energy in chemicals. And when I connect something to the two terminals of the battery, the electrons get pumped around a circuit, may make a light bulb glow or an electric motor turn. So you can think of a battery as an electron pump, which pumps electrons round and round, just like a water pump can pump water round and round. Well, how do we make all that work in these things called capacitors? Well, if ever you come across an old capacitor, try opening it up and you can see what it's made of. And I'm going to make a capacitor now. Thank you, Sonem, for having separated our charges. And now if you go away, do you know what's going to happen? They're all going to rush together again, because positive and negative charges attract each other. And as soon as you've stopped separating them and go away, whoomp, they'll all come together again, because positive and negative charges attract each other. So let's make a capacitor. To make a capacitor, you need a paper towel, a piece of paper from the paper towel, and you need 2 pieces of aluminium foil. 1 piece of aluminium foil, 1 piece of paper, and another piece of aluminium foil. So what we have got in physics language is 2 sheets of conducting material separated by a sheet of non-conducting material. And there is a capacitor. These are the 2 conducting plates. This is a piece of non-conducting material. Now it can be paper, it can be plastic, it can be glass, it can even be air. You can have an air capacitor. But let's make our capacitor out of 2 sheets of aluminium foil and a piece of paper towel. There's the capacitor. Now you may say, but hang on, this doesn't look like anything here. Well, of course it doesn't, because we're not going to go around with that in your mobile phone. What we're going to do is make it smaller by folding it. And what we're going to do is put another piece of paper towel on top, and then we are going to fold it over like that. So you notice the sheets are still separated from each other. And then let's put another piece of paper here to stop the sheets touching each other. And then we will roll it up like that. And then we'll put it in a little aluminium box, and there we have our capacitor. So if you open these up, what you would find is a sandwich. 2 sheets of conducting material separated by a conductor. Separated by an insulator. And in my case, the insulator is a paper towel. In physics, the material in between the 2 plates, the insulator, is called the dielectric. So the 2 sheets of conducting material are separated by a sheet of dielectric. And we can fold it all up and make them very, very small. Here it's all the same, and we can actually make them in multi-layer capacitors. So conductor, insulator, conductor, insulator, conductor, very expensive on paper towels, which are difficult to get these days because of coronavirus. Everybody's bought all the paper towels. Insulator, conductor, insulator, and then I'll wrap it all up into a nice little folded thing, and I've now got a capacitor with 4 conducting sheets and 3 sheets of dielectric in between. So I can make capacitors have many, many layers. Now, what happens is this. The electrons and the protons end up on one sheet and the other. So if we just take our 2 conducting sheets again, when I connect this, and if I had a battery, I could connect those 2 sheets of aluminium foil to the battery. One sheet would be connected to the positive, one to the negative. This one, the positive one, all the electrons would be attracted onto here. This one, the negative one, all the positive charges would go onto here. This one, the negative one, all the electrons would go onto here. So I'd end up with too many protons on here, not enough protons on here, positive charge on there, negative charge on there. And that is a capacitor. And how is it storing energy? It's storing energy through separation of the charges, creating an electric field. So whereas my ordinary little battery stores energy by chemicals, a capacitor stores energy by separation of electric charge. And I make those charges separate by providing a source of energy, like connecting them to a battery, which pumps the electrons from one conductor to the other. A battery is an electron pump, pumping the electrons from one side to the other. So that is a capacitor, and it stores energy by separating the electric charges. So I said that what a capacitor does is store energy. The reason why I say it doesn't store charge is this. If I look at these 2 sheets of metal with the insulator in between, the dielectric, at the moment there are a balance of positive and negative charges on each plate, just as if I had 2 bags of multicolored sweets there. When I separate them, I take electrons from one side to the other. I take electrons from one side to the other. Notice it's electrons that move, not protons. If protons move, the whole sheet of paper would move. It's the electrons that are pumped by a battery, for example, from one side to the other. So if I look at the capacitor as a whole, the amount of charge has not changed. It hasn't stored more charge. It has simply redistributed the charge, the negative charge, from here to there. So this becomes positively charged and this becomes negatively charged. So a capacitor stores energy in the form of separated charges, or if you like, in the form of an electric field. The amount of charge on the capacitor has not changed. And that's sometimes a common misunderstanding when you read that capacitors store charge. They actually store energy by separating the charge. Now, how much energy can you store in a capacitor? Well, that depends on 3 things, which we can see here. The first thing, the amount of energy you can store in a capacitor, in other words, its capacitance. The first thing the capacitance depends on is the surface area of the plates. The surface area, length by breadth, the surface area of the plates. The second thing the capacitance depends upon is how thick the dielectric is. How thick is that piece of paper? The thinner the dielectric, the more energy you can save on the capacitor. The thinner the dielectric, the greater the capacitance. So what we aim to do is to have a big area of plates and a very, very, very thin insulator in between them. And in fact, modern capacitors, such as you might find in a computer or a mobile phone, they have a thin, a couple of atoms thick layer of dielectric in between, so that this is very, 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 very thin, 1/1000th of the thickness of one of your hairs. The third thing that the capacitance depends upon is what is the dielectric made of. And I mentioned it can be made of paper, a paper capacitor. It can be made of glass. It can be made of plastic. It can be made of quite a number of things as long as they are insulators. In fact, some capacitors are called air capacitors, and they are just two plates separated by a layer of air in between. So the energy you can store in a capacitor, the capacitance, depends on the size of the plates, the area of the plates. It depends on what the insulator in between is made of, and it depends on how thick the insulator is. Bigger area, bigger capacitance. Thinner dielectric, bigger capacitance. And then the material affects it as well. There is a figure called the dielectric constant of a material, which affects the ability to store energy. So let's now think about an analogy. I don't know whether you got the idea. We separated the sweets. Let's take 2 glasses of water. The water level in each is the same. It's all balanced out. The whole thing is in equilibrium. And if I join those 2 glasses of water with a tube, nothing will happen because the water is at the same level in both. I don't want to break my glasses, so I'm now going to go to plastic bottles. And you can try this yourself if you like. If you were to take 2 plastic bottles, you will see that in this bottle, the water is at a higher level than in this bottle. At the moment, the bottles are separated. Think of these as the 2 metal plates of a capacitor. This has got too much positive charge. Sorry, let's put it the other way round, shall we? This has got too many electrons on it. This has got fewer electrons on. Now, if I connect them with a wire, the electrons will flow through the wire until the water is level on both sides. If I take a little plastic tube, rather a big one, I'm afraid, it's all we could find. If I connected those 2 bottles of water with that plastic tube, water would flow down from that through the pipe and up there until they were level. So if you think of that having too many electrons, that having not enough, the electrons would flow through there and up there. And as they flew through here, I could actually put a little bulb in the way, and they'd flow through the bulb, and they would light up just like my face in the middle is lit up when the electrons move from one bottle to the other. So that is how a capacitor can store energy. Too many electrons, not enough electrons, connect them, whoosh, a flow of electrons goes through a bulb, lights it up until the water level is equal on both sides. So that's what happens when you discharge a capacitor. Now, if I started with the water level on each side, I could put a battery here, and I could pump the water into there. It would go down there, it would go up there. So I've stored energy because the water is not at the same level. In a capacitor, I store the energy because there are more electrons there than there are there. So that's how the electrons store energy. You can try that yourself with plastic bottles of water. You can do an enormous number of physics experiments with an empty water bottle and some water. Very, very useful for demonstrating. And so, the capacitance of a capacitor represents its ability to store energy. And the capacitance of a capacitor is measured in a funny unit called a farad, named after Faraday. Faraday was a great electrical engineer who invented Faraday's laws. Faraday we have to thank for everything we have that works by electricity now, because it was Faraday who discovered that you could make a generator and you could use an engine to turn the generator, and out came electricity. We have Faraday to thank for our hydropower stations. Water is used to turn the generator and we get electricity out, which lights my lights here. So Farad, named after James Faraday, a very great electrical engineer with so many discoveries. And so we measure capacitance in farads, but a farad is an enormously big capacitance. In fact, the capacity of the whole Earth is just a few farads. So if I look at a typical capacitor, like those that appear on my screen here, these are microfarads. In other words, if we look on this, we see it's so many 47 microfarads, which means millionths of a farad. So most ordinary capacitors are millionths or even billionths of a capacitor, of a farad. Capacitance is measured in a unit called a farad, capital F, but a farad is an enormously big unit of capacitance. In fact, the capacitance of the whole Earth is just a few farads. So real capacitors that we get, for example, the one here on my screen, you'll see that it is microfarads, 4,700, and I don't know whether you can see it, but you'll know the little symbol there is mu, the Greek letter mu, mu f, microfarads, millionths of a farad. And some capacitors will be picofarads, millionths of farads. So you will never come across a 1 farad capacitor. Now, when you separate out the charges, you generate an electric field. Negative, positive, there's an electric field. And therefore you get a voltage between the two plates. So we need to know about a capacitance, we need to know 3 things. Number 1 is the size of the capacitance, F. Number 2 is how much charge has been separated. We'll call it Q. It'll be minus Q there and plus Q there. Remember, the charges have separated. Minus Q on here, plus Q on there. And that will generate a voltage between the plates of voltage V volts. So Q, quantity of charge separated, C, the capacitance of the capacitor, and V, the voltage across the plates of the capacitor. And there is a very simple relationship. How do we define the capacitance of a capacitor?